Okay, so here we are. We're going to start our video here on vectors and scalars. Vectors are something that are certain quantities that have both magnitude and direction. Okay, whereas scalars are quantities that have magnitude only or size. Some examples of vectors. Okay, so let's think of some of them. A vector is something like velocity. And through the year, I want you to continue writing these down. Displacement. All right. And some examples of scalars, speed, and distance. So throughout the school year, remember to continue this list, or at least keep in the back of your mind the difference between vectors and scalars, but somewhere you should really have a list of the different vectors and scalars. So notating vectors, how do we go about writing them? Okay, so this is how you notate a vector. Just make sure you show the vector with a arrow over it, and here's how you draw a vector. Just an arrow with an arrowhead and tail. Here's a problem that we're going to solve together. Okay, now you have on your sheet the generic way of solving these problems, or the formula or steps in which we would go about solving a problem like this. So let's solve this one together. It says that we've got our particular vector that goes 40 meters, okay, in the positive x direction. So that would be directly to the right or at 0 degrees. Then it goes about 100 meters at 53 degrees. And then finally, it says it goes 50 meters, 37 degrees below the x-axis. So we'll start there. So if we had an x-axis and we had to go below it, we would go like that. Okay, and this would be 50 meters. Obviously, this is not to scale. And this would be here. Right here is where, here's the 37 degrees. Okay. So what we're going to do is we're going to use this little setup here to look at how to solve for the horizontal and the vertical vectors. So the equation, just think of it as the vector z is the vector, let me fix that. It should be, for the horizontal, it would be x is equal to z cosine theta, and in the vertical, it would be y is equal to z sine theta. So what we will do is we'll plug those values in for each equation. So in the horizontal, we will take 40 meters and calculate out, multiply that times the cosine of 0 degrees, which turns out to be 40 meters. Then 100 meters, cosine 53 degrees, that gives us 60 meters. 50 meters, cosine 37 degrees, and that would give us 40 meters. And that's supposed to come out as 140 meters as we add them up. So that's our next step. We add up all the horizontals. Then we do the same thing in the vertical. We take 40 meters and we multiply it times the sine of 0 degrees. And since the sine of 0 is 0, we would get 0 meters there. And then 100 meters and multiply that times the sine of 53 degrees, and we get 80 meters there. And then, because this final value is going to be negative, and let's look at why that's negative. If we look at this final setup here, or this last vector, the horizontal is in the positive direction, it's to the right, and the vertical is downward. So this is going to be a negative value. So I'm going to put a negative 50 meters times the sine of 37 degrees, and that'll give us negative 30 meters. If I add all these up, I get 50 meters. So there's my 50 meters, there's my 140 meters. This is in the vertical, and this is in the horizontal. So what I then do is I take these values and I pretend I'm at the origin, and I go to the right 140 meters, because it's positive, and then I go upward 50 meters, because that's also positive, and I want to find this resultant vector right there. So I would use a Pythagorean theorem, and I would take the square root of 140 squared plus 50 squared, and I would get an answer there of about 150 meters. So there's my resultant length, and I would also need to get this angle here. So that angle theta would be the inverse tangent of the opposite side, which is 50, divided by 140, and we get an answer of approximately 20 degrees. So we would say that the resultant vector is 150 meters at 20 degrees. Okay, any change in velocity over a period of time is called acceleration. And the positive negative sign of acceleration indicates the direction of the acceleration. And acceleration can be either an object speeding up, slowing down, or turning. Basically, any change in direction would be acceleration or change in the speed. So if the acceleration is 0, what does this mean about the motion of the object? Well, then that would mean that the object would have, oops, get my pen here. That would mean the object would have constant velocity. And that constant velocity could either be a 0 constant velocity, a positive constant velocity, or even a negative constant velocity. Is it possible for a race car circling a track to have 0 acceleration? No, because remember what we said, if an object is turning, then it's accelerating because it is changing direction. So any change in direction, or any speeding up or slowing down is an acceleration. So no, because it's always changing direction. Okay, so the simplest form of acceleration is uniform or constant acceleration. Acceleration which is uniform can be calculated by using this equation, delta v over delta t, and the unit for acceleration is meters per second squared. Okay, if the sign of the velocity and the sign of the acceleration is the same, the object is speeding up. So let's go back to our motion maps. So if I've got, okay, so let's say we've got a velocity that's a 0 velocity at the beginning, and then it starts to pick up speed. Okay. Because the change in velocity is the acceleration, this velocity has changed from this previous velocity by about that much. And this velocity changed from this previous velocity by about that much. And this velocity changed from that previous velocity by about that much. So these are what we would call the acceleration vectors. So velocities that are increasing would have accelerations in the same direction. So likewise, if I had a velocity that was 0 but was picking up speed in this direction, my acceleration would still be in the same direction. However, if the sign of the velocity and the sign of acceleration different, the object's slowing down. So let's look at an example of that. So if I had an object that was already moving relatively quickly, here's what would happen to the acceleration. So the change in this velocity from this previous velocity would be about that much. It points in the other direction. And the change from the previous velocity to that velocity would be that much. And so would that change. So the acceleration points in the opposite direction when the velocity is slowing down. So we're going to have some different demonstrations here. These we will go over in class. Okay, now here are the kinematic equations. You need to memorize these equations. Write them down now, and then you're going to have to memorize them later because they are that important. Okay, so write these down as we solve some of these problems. Right now, what I'm about to explain to you here, or what I'm about to show you, is what we call the kinematic strategy. You should be using the strategy for just about everything we do in physics. So in this problem, it says a horse is running with an initial velocity of 11 meters per second and begins to accelerate at negative 1.81 meters per second squared. How long does it take the horse to stop? So with our strategy, we always start off with a motion map. So this motion map would look like this. It's already moving 11 meters per second, and we're assuming positive is to the right. So let's start off with a velocity vector like that, and its acceleration is negative. So if it's a negative acceleration, we know that the object is slowing down. So we've got, we know it's slowing down because the velocity is positive and the acceleration is negative. So whenever there are different signs, we know the object is slowing down. So the acceleration we know would point in the opposite direction, and that makes sense because we said that acceleration would be negative if it's to the left, and our velocities are positive because they're to the right. So there's our motion map. The next part of our strategy is to write down these variables. So always write down these variables: x, v initial, v, a, and t. There are 5 of them. And then what we're going to do next is we're going to see if any of these variables are known in the problem. So x, the displacement, we don't know that. The initial velocity we know to be 11 meters per second, and I'm going to emphasize that it's to the right. The final velocity, well, we can look at our motion map, and we know that that's 0 meters per second. So that's one way that the motion map is helpful for us. The acceleration is also given to us, negative 1.81 meters per second squared. The time we do not know. So in order to solve these kinematic problems using the strategy, we need to have 3 variables that we know and 1 more that we're looking for. It says, how long does it take the horse to stop? Well, that's the time. So those are the 4 the 4 variables that we need in our equation. So what we need to do is we need to go back and find which equation has all 4 of those variables. And it turns out that the equation that has all 4 of those variables is this one right there. So let's go back and let's look at our equations, or let's write down that equation, v equals v initial plus at. And we know we're solving that for time, so algebraically, I would solve that for this equation for time, v minus v initial over a. So my final velocity, just like it says here, is 0 meters per second. My initial velocity is 11 meters per second. And I'm dividing that by acceleration of negative 1.81 meters per second squared. And I'm getting a time of about 6.08 seconds. Okay, so there's how we're using our strategy. Let's look at another example of how to use the strategy. In this example, it says on a ride called the Detonator at Worlds of Fun in Kansas City, passengers accelerate straight downward from 0 meters per second to 20 meters per second in 1 second. What is the average acceleration of the passengers on this ride? So what we do again is we want to start with a motion map. So here's my motion map. We're starting off with a velocity of 0, so we're going to use a dot. Then velocity is increasing on the way down. So these velocities are obviously going to be negative. Because the velocity arrows are increasing, my acceleration arrows should be in the same direction. So there's my motion map. Now let's write out the rest of our strategy. X, v initial, v, a, and t. So we don't know the displacement, the initial velocity, 0 meters per second. We can tell that by looking at our motion map. Okay, we know starting at 0. The final velocity, the problem tells me it's going 20 meters per second, but my motion map shows that it's going downward, and for us, downward is negative. And then our acceleration, we don't know. Our time, it tells us, is 1 second. So we circle the 3 variables that we know, plus the one we're looking for, which is that variable. So that means we're going to use this equation again, v equals v initial plus at, but this time we will solve it for the acceleration, which is v minus v initial over t. Our final velocity we said is negative 20 meters per second. Our initial velocity is 0 meters per second, and that's a time of 1 second. So we get an acceleration of negative 20 meters per second squared. The next part of the question says, how fast will they be going if they accelerated for an additional second at this rate? So again, we're going to it's still the same motion map. So now what we will do is we will complete the rest of our strategy here by looking at what we know and what we don't know. So still x is our unknown. Our v initial is 0 meters per second. Oh no, our initial velocity now is negative 20 meters per second. Because now we're starting at this part. So we know that this is negative 20 meters per second. So this is getting even longer down here. We want to know how long that takes. So the final velocity, how fast are we going? That's our unknown. Our acceleration is going to accelerate at the same amount. That's the assumption we've got to make, negative 20 meters per second squared. And that would be a time of 1 second later. So 1 second after it's going negative 20 meters per second, how fast will it be going? Well, some of you can probably do that in your head, but let's show how we can still use our strategy, again with this exact same equation, to solve for that problem. So we know that our velocity, our initial velocity is negative 20 meters per second now. Our acceleration is negative 20 meters per second squared times a time of 1 second. So this gives me a final velocity of negative 40 meters per second. Okay, so this problem we will do in class. Let's start this next part by looking at some graphs in 1 dimension. So these are some things that we're going to look at in class, how we can do these things. You could maybe try to figure those out beforehand, but if not, that's okay. One of the things that we're going to learn is that for a position time graph, the physical feature of the graph that gives the constant velocity from A to B would be its slope. Okay, so the slope of a position time graph gives us the velocity. Alright, so say that to yourself. The slope of a position time graph tells us the velocity. Alright, so let's solve that in this particular problem here, where we want to find the average velocity from this graph. So if we want to find the average velocity from a position time graph, we need the slope. So let's calculate this slope as the rise over the run. Okay, I'm going to look at 0 from 0 seconds, that spot right there, to 6 seconds. So the rise there is a positive 2 meters, and the run is 6 seconds. So we get a value of about 0.3 meters per second. Okay, so these are some other things that we will do in class. Make sure we understand them. Okay. Question is, can you determine the average velocity from the time at point A to the time at point B from this graph? So remember, average velocity just depends upon the ending point and beginning point. So certainly what we can do is we can take just this point here and this point there and draw the best straight line that we can draw through them and calculate out that slope, and that would be our average velocity. So in this particular problem, there's some estimating here, so that's what we will do. It says determine the average velocity between 1 and 4 seconds. So at 1 second, we're right about there. And then at 4 seconds, let's say we're right about there, just about in the middle. So our average velocity, like we said before, just depends upon the two endpoints, the change in position over the change in time. So the average velocity is equal to 1.5 meters. So right there we're about 1.5 meters minus 1 meter over 4 seconds minus 1 second. And so that gives us a value of just about 1.7 meters per second. Okay, so instantaneous velocity is our next topic. The instantaneous velocity is a velocity at a single instant in time. So the way we find the instantaneous velocity is by finding the slope of a tangent line. So if I want to find the velocity right at that instant, I would sort of estimate a tangent line, and then I would have to calculate out the rise and run of that tangent line. So again, there's some estimating with this. So if we wanted to find the instantaneous velocity at 1 second, that would be right about there. So to find that slope there, I would draw a line that would just go straight through it like that. Okay. It's not a perfect tangent line, but you get the idea. So the velocity, like we said, is the change in the position over the change in position over the change in time, okay, which is essentially the slope. So the slope of this line, I'm going to look at that point and that point there, those 2 points, and my velocity would be equal to 2 meters minus 0 meters over 2 seconds minus 0 seconds, and that would give me a value of about 1 meter per second. Okay, so graphical problems, again, we'll go over these in class. More problems go over in class. Okay, continuing with our graphing. So this is a velocity time graph, and we're asked what physical feature of the graph gives acceleration. Well, for a velocity time graph like we've got here, the slope gives us the acceleration. So the answer to what physical feature of the graph gives us the acceleration is the slope. So the slope of the velocity time graph is equal to the acceleration. So the acceleration is the change in velocity divided by the time. It says there. Okay, now we want to determine the acceleration from this particular graph. So the acceleration we know is a change in velocity over the change in time. So in this case, if I take this position here at 20 meters per second as a final position and this as the initial position, I can say that the final velocity is 20 meters per second. I'm going to subtract the initial velocity, which is negative 20 meters per second. The change in time, the final time is 4 seconds, and the initial time is 0 seconds. And therefore, our final velocity, our acceleration, will be 40 meters per second divided by 4 seconds, or 10 meters per second squared. Another example problem asks us to determine the displacement of the object from 0 to 4 seconds. So what we need to know here, one of the really important things to know here is the fact that the displacement from the velocity to time graph, so we can get the displacement from a velocity time graph we can get from the area. Okay, so the displacement of a velocity time graph is the area. So from 0 to 4 seconds, if I look here, I've got this first area. I want to calculate out that first area from 0 to 2 seconds. Then from 2 to 4 seconds, I've got this area. So let's calculate out this area first. That area there, since it's a triangle, I have to calculate out 1/2 base times height. I know the base from there to there is 2 seconds, so 2 seconds. The height from there to there is a negative 20 meters per second, so that gives me a negative 20 meters. That's the displacement for the first part. Then for the second part, this part here, I once again use 1/2 base times height. So 1/2 the base is 2 seconds. The height is 20 meters per second. From there to there is 20 meters per second. So I get a displacement for that area of 20 meters per second. So if I take these two displacements and I add them up, 20 and negative 20, I get 0 meters. This question asks here, how would you describe the motion of this particle? Well, it's got a constant slope, and the slope on a velocity time graph tells us the acceleration. So the acceleration must be constant. So constant acceleration. So in class, we're going to draw these graphs out. Save that for class time. Okay, what we're going to do now is we're going to apply the kinematic strategy to a gravity problem. So let's look at what's going on in this particular problem. It says you drop a ball from rest off a 120-meter high cliff, assuming air resistance is negligible. How long is a ball in the air? So we'll draw the velocity vectors first. It's obviously going to start with no velocity, then pick up some speed on the way down. So those would be the velocity vectors. Because the velocity arrows are increasing, the acceleration arrows should point in the same direction. So our acceleration arrows would point downward. Now, one of the things that we should have known or found out was that the acceleration due to gravity, we also label as little g, anywhere near Earth is always negative 9.8 meters per second squared. So that's always going to be true for any object in free fall, like this problem is. So we'd write out our x, v initial, v, a, and t as part of our strategy. X we know. Let's label some things here. At the top, if we label the very, very top of this cliff 0 meters, because downward is negative, down at the bottom here, we would actually be at negative 120 meters. So our final position x here would actually be negative 120 meters. Our initial velocity would be 0 meters per second because it's starting with no velocity. The final velocity we don't know, and acceleration due to gravity is always negative 9.8 meters per second squared. And our time is something we don't know as well. So remember, as part of our strategy, we circle the variables that we know. We know these three variables, and we're looking for how long it's in the air, so that's time. So the equation that has all four of these variables would be this one here. X is equal to x initial plus v initial t plus 1/2 at squared. We know the initial position is 0. We've said that already. The initial velocity is 0. We've said that over here. So the equation, because x is equal to 1/2 at squared, if I solve that for t, now you can do this math yourself, the algebraic manipulation to find that t is equal to the square root of 2x over a. I'll find that when I plug that in, I plug in 2. For the final position, I'm going to plug in negative 120 meters. And then I'm going to divide that by the negative 9.8 meters per second squared. and I get a value of approximately 4.9 seconds. Okay, the next part of the problem says, what's the ball's speed and velocity when it strikes the ground at the base of the cliff? So at the base of the cliff, we know that position again is negative 120 meters. Right, we don't have to redraw the motion map because the motion map is fine the way it is. Initial velocity is still 0 meters per second. The final velocity is unknown. Okay, that's what we're looking for. The acceleration is negative 9.8 meters per second squared. And the time we actually know now, that we know that that's about 4.9 seconds. So in this case, we know 4 of the variables, and we're looking for the 5th one. So the easiest equation there, we can use a couple of equations, but the easiest one would probably be this equation, v equals v initial plus at, where our initial velocity is 0 meters per second. I'm going to add negative 9.8 meters per second squared times a time of 4.9 seconds. And we get a value there of 48 meters per second negative. Now that would be the velocity because that gives us the direction. But if we were just looking for the speed, we would leave the negative sign out and just say 48 meters per second without any positive or negative in front of it. And the sketching of this, we'll do that part in class.